Right, so we'll continue with our study of linear and angular momentum. At the end of the last segment, we defined what these quantities are for continuum bodies, and we also observed that there is this additional quantity which makes its appearance, the center of mass. Okay? So now let's use these to write out the balances of linear and angular momentum. Right? And this essentially means we need to write out their rates. Okay, so so we're talking here of continuum bodies now. Okay, so the linear momentum then is L function of time equals integral over omega naught rho 0 function of position, v function of position and time dv, which can also be written without any change in definition as an integral over the current configuration, right, involving the spatial density and the spatial velocity. Okay, now we want to talk about the rate of change of this quantity, right, which is L dot. Okay, now we're going to use our current configuration to make our arguments mathematically here. Okay, and this means that we want to calculate d dt integral over omega t. I'm going to suppress variables here. Well, maybe not. Maybe I'll write everything. Okay, now here is our first use of our Reynolds transport theorem in the derivation of balance laws. We showed in our manipulations of the Reynolds transport theorem that whenever we have this type of an integrand involving the mass density multiplying another spatial function, right, we saw that when we take the time derivative of this sort of an integral, this is equal to integral over omega t, right, just rho times the material time derivative of v. Remembering now that x is got from the motion, right? All right, and this derivative that I've written out there is not just the simple partial time derivative, it is actually the material time derivative, right, which we defined some time ago. Okay, which is also, of course, we know that this is essentially our definition of the spatial acceleration. All right, so here we have it. This is our formula for the rate of change of linear momentum of a continuum body. Okay? And just for convenience, let me also perhaps write it using the acceleration. Okay? And then recalling that this product is dm, right, the elemental mass. We see our connection here with the rate of change of linear momentum of a particle, right? We've essentially got the rate of change of momentum of every elemental mass dm, right, as written as that mass dm times its acceleration, integrated over the body to collect all the mass. All right? So we have this. Let's plow on now and write out the equivalent rate for angular momentum defined about the origin. Okay, so for angular momentum we have recall that we have J naught. Okay, and the naught or the O or 0 reminds us that this is angular momentum about the origin. Okay, it's x cross rho x comma t v x comma t dv. All right, in the previous segment, we saw why it's important to only treat this as an integral over the current configuration. All right. Of course, there are some of these variables could be mapped back to the reference configuration, but it does not make sense to replace little x with capital X, because that would be changing the type of angular momentum we're looking at. We would essentially be looking at only the initial angular momentum, which is not what we want. All right. I'm just for convenience, I'm going to write this out as this, by simply moving the position of some of these variables here in the integrand. Okay, the reason for doing this is now when I write it out in this form, when I want to compute J naught dot of t, I'm going to say that it is d dt of this integral. Okay, and once again, our use of Reynolds transport theorem becomes very straightforward, because again, I've written out the integrand as the mass density multiplied by a product of two spatial functions, okay, which is just another spatial function. All right, so Reynolds transport theorem tells us, okay, that this quantity is integral over omega t rho x comma t. The material time derivative of this cross product, okay, remembering that we are looking at x obtained from the motion, right, little x obtained from the motion, okay, and this comes to us from the Reynolds transport theorem. Okay, I've abbreviated transport and theorem, short forms of them. Okay, all right. But we know how to compute that derivative. It is just the following, right? We have rho just comes along. Okay. Now that time derivative gives us two terms. Right? The first is going to be the time derivative of x, but that's just the velocity, right? So we have x dot, which I will straight away say is just the spatial velocity crossed with v, all right, plus x cross the material time derivative of the velocity. Right? But then we saw, and we invoked the condition on the previous slide, we said that, well, this is just the spatial acceleration. Okay? Maybe I'll write it as v dot. No, I should not write that as v dot. Let me just write that as a. Okay? The spatial acceleration. Right? D little v. Okay. And now here in this case we have a vector crossed with itself, v cross v, which is 0. Okay, the 0 vector. All right, so what we see then is that J naught dot equals integral over omega t rho x comma t little x cross a. Okay. And once again, observing that this product, rho dv is dm, we see that this rate of change of angular momentum of the continuum body is obtained by simply looking at the rate of change of angular momentum of each elemental mass dm. Okay, because this product dm times the acceleration, right, is the rate of change of linear momentum of that elemental mass dm, right, with x crossing it. Okay. All right, so this is how we get the rate of change of angular momentum of the total continuum body. Let me state that as a remark for both. So L dot is the integral of change of linear momentum of each elemental mass dm, right? And likewise J naught dot is integral of rate of change of angular momentum of each dm. Okay, I've essentially written out in words what those integrals are, but hopefully it gives us a little more physical insight. Okay, and then along come Newton and Euler and say, well, they say that L dot is equal to F, all right, and likewise they say J naught dot. Now, in this case, we cannot quite write J naught dot as a simple cross product of the position vector and the force, simply because the body has its mass distributed. Okay, so it's not quite as simple as that. But instead, let us just say that it is equal to the resulting moment. Okay, m naught. All right, so this is the moment. Right. Let's, however, in order to prepare ourselves for what's coming up in a few more segments, let's write out the form of the force and the total moment, the total force and the total moment on continuum bodies. Okay? So, here's the situation that we are faced with. We have the body here, and I'm writing it in its, I'm showing it to you in its current configuration. The question I want to ask is, how do we write out the total force acting on this body? In mechanics, the forces acting on a body, the external forces acting on a body, can be separated into two types. One is the idea of there being a force that's distributed over every volume element of this body. All right? An example of that is the gravitational force. Right? Because the gravitational force acts on every little elemental mass, effectively every little elemental volume, all right? And that gives us a total force if we integrate that over the body. And in addition, we may be applying externally a traction on certain parts of the surface, right? Like this is a traction vector. This arrow represents a traction vector. You may think about it as a force distributed over some region of the surface of the body. Okay, so we have volume forces distributed throughout the volume and surface forces. Okay, so the external force. Okay, write it as F, function of time. Okay, it is the integral over omega sub t, right, of a quantity which I am going to have to use a new symbol for, and I would rather use F, but let's suppose that in place of F we use, let's suppose we use B sub F. Okay, so that is for body force. Okay, that is a force defined per unit volume, integral dV, plus an integral over a certain subset of the surface. Okay, it's not going to be necessarily written over the entire surface. It's going to be over some subset of the surface, so I'm going to introduce yet another subscript here. I'm going to use a capital subscript T, where that T is for traction. The capital T is for traction. Okay? And here we are going to write T dA. Okay? So this is volume, or what are sometimes called volumetric body forces, and this represents surface tractions. All right. Now observe that in both cases we've integrated out the spatial dependence through the integral over the volume in the first integral and the integral over the surface in the second integral. Okay? So now these are only functions of time. These can only possibly still be functions of time. All right? Okay. We'll revisit this in much greater detail as we proceed, but I just wanted to put this up. All right. And likewise, we write out the external moment. We decided to use capital M naught function of time. It is simply the moment induced by each of these force distributions. Okay? So we have integral over omega sub t. We have little x cross body force d little v plus the same sort of effect from the surface tractions. Little x cross little t dA. Okay. Well, I'm not going to write what they each are, but it should be clear from the previous equation. Okay. So the moment's contributions from each of these external force distributions. Okay. Right. So we have this, and essentially the equivalence, the relation between the rate of change of linear momentum and the force is that the rate of change of linear momentum is equal to this force. Okay. So what we see here then is maybe I draw a line here and I say that we have L dot function of time equals this force as defined here. And we also have J naught dot as a function of time equals this moment.